designation or recognition of being one of the hardest working students in the group. He did, I think, the most experiments ever, filled 3 notebooks full of experiments. And today, he's going to tell you a little bit about what he's been doing these last 4 years. So with that, I'll leave it to you.
Thank you everybody for coming to my talk. This will be my PhD defense. So I have worked on this for 4 years. I'll try to give you some glimpse from all those experiments, all the analysis, and all the things we have done these 4 years. But this will be a glimpse. So what we did, we have studied quantum diffusion controlled chemical reactions inside a quantum solid. Actually, we have used 2 quantum solids for this study. So you'll hear a lot of quantum today, and I'll try to bring some stuff here, what we have learned in textbook about quantum mechanics. So in this talk, I'm lucky that here at the University of Wyoming, I have worked in the coolest group in Wyoming. So why we're the coolest group? Because I made a plot here, why we're the coolest group. So if you think about the temperature, I mean, I still use degrees Celsius, so I'll be using degrees Celsius or Kelvin today. So here you see that's 38 degrees Celsius. That's like the best temperature for human body to, have problem. Your immune system works best. All the bacteria, virus works best at this temperature. But if you wanna slow down those processes, because this processes to me is chemical reactions. So to slow down chemical reactions, we cool it down. So if you buy some grocery from Walmart, you put them in refrigerator because you wanna slow down the rotting process. If you put them in refrigerator, that's like 2.5 degrees Celsius. But if you wanna really keep it for longer, you put them in deep freezer where you put mostly meat or fish and stuff. But if you wanna really slow down, in some groups, you use liquid nitrogen to really cool it down, slow down the chemical process. But in our group, we want to see the limit. We want to cool it down to real cold, like 4 Kelvin. So that's very close to the 0 Kelvin, 0 temperature or 0 heat of the universe. So we cool it down to 4 Kelvin. So that's our high temperature. We call it high temperature. And we also cool it down to 1.6 Kelvin. So that's our low temperature. So when I say today low temperature, that means 1.6 Kelvin, and high temperature 4 Kelvin. That's why, and we are the only group in Wyoming who can do experiments or do stuff at 1.6 Kelvin in experiments. So that's why we're the coolest group. So in our group, we actually study matrix isolation spectroscopy. We do. Here, what I will be talking today is, in this slide, I will give an overview or introductory slide where I'll be talking what I may not gonna talk today. So in our group, we study 2 kinds of chemical processes, photolysis and chemical reactions, and also we study nuclear spin relaxation of different molecules. So I was mostly focused on this portion, photolysis and chemical reactions. And you see, we have done a lot of chemical reactions over these 4 years. So these are very fundamental chemical reactions. Any jet chemistry students will be very happy because you don't need to balance these reactions. There's a simple like oxygen atom, oxygen molecule to make ozone. So I have studied all of these as lead or co-lead. Every experiment is a project. So a lot of projects. Then that was in solid parahydrogen, but we also studied in solid orthodeuterium, these 2 projects. And we did some spectroscopy. We published a paper on spectroscopy of these 2 molecules. I also worked on some liquid spin relaxation in solid parahydrogen and solid orthodeuterium. So a lot of things. But these are the projects where I was co-lead. I was not the lead. So I will not be talking today about any of these projects. Then there are two projects which I will not be talking today because there's also two big projects. So I'll be focusing on only these three: oxygen atom in solid parahydrogen, oxygen atom in orthodeuterium, and chlorine atom in solid parahydrogen. So I will only be talking about these three projects. So that's why I am refining my talk title. So all those atoms, chlorine, oxygen, they are heavy atoms. So my talk will be heavy atom quantum diffusion control chemical reactions in solid parahydrogen and orthodeuterium. So we'll be studying these three we'll be talking about these three reactions. So yeah, as we'll be talking a lot about quantum mechanics and quantum timing and everything, so let's start with Heisenberg. Not with this fake one, the real one. So the real one, he won the Nobel Prize in 1932. And if you read his Nobel announcement, you see that he developed quantum mechanics which led to discovery of allotropic forms of hydrogen. What are those allotropic forms? Those forms are, if you want to make a hydrogen molecule, you need two hydrogen atoms, right? So if you bring two hydrogen molecules close together, if you bring two hydrogen atoms to make a hydrogen molecule, you need two nucleus of hydrogen. So if you look at the spin of that nucleus, you see that two nucleus could be parallel or anti-parallel. So if they are parallel, we call it orthohydrogen, which can access the higher energy, but lowest energy can only be accessed through if you have opposite spin of those two nucleus, and that we call parahydrogen. Same statistics goes for deuterium, so you can have paradeuterium and orthodeuterium. So let's just focus for now on parahydrogen and orthohydrogen. So parahydrogen, because of some statistics, it has the lowest energy state, that's by 120 Webb number. So in our group, we want to study things in solid parahydrogen, not orthohydrogen. So I'll be focusing on parahydrogen a lot today. So if you have a parahydrogen molecule, that looks like an s orbital. So it's spherically symmetric. If you look at the de Broglie wavelength of that hydrogen molecule, that's lambda, that's bigger than the actual molecule, the hard sphere. So that sigma will be the hard sphere. So the lambda is bigger. So if you divide lambda by sigma, we call it de Boer parameter. So its wave function is bigger than its actual size. So that gives us a new parameter, de Boer parameter, that actually tells us if it is quantum mechanical or not. So if you see the de Boer parameter of different solids, you see that helium is best quantum mechanical because de Boer parameter is about 2. But for solid parahydrogen, that is like 1.2. And for orthodeuterium, that's like 0.9. So orthodeuterium is also quantum mechanical, but less quantum mechanical than solid parahydrogen. So if you make a solid, you need to bring together all the all the hydrogen molecules together. If you bring them together, as their size can allow them come to closer, so they will overlap in their wave function. That's why it makes a solid, quantum mechanical solid. It's a solid, but it acts like liquid, so it has some flexibility inside, because at very low temperature, it still has the very big 0-point motion, which is like 18% of its size. So it can wiggle at the position where it sits. So as we have a quantum mechanical solid, what we can do? We can study chemical reactions, we can do photolysis inside that. But before going into quantum mechanical situation, let's think about what classically it would be. So if you think thermal diffusion inside a solid, so if you have solid parahydrogen, and if you want to have some diffusion process, thermally activated or thermal diffusion, in classical sense, you can use this expression to get the diffusion coefficient. And you see, it's hard to see from 0.300 Kelvin, so let's zoom into 0 to 14 Kelvin. So below 8 to 9 Kelvin, you see that diffusion coefficient is almost 0. So if you put something, it should not diffuse at this temperature, below 8 or 9 Kelvin. Above 9 Kelvin, it starts to diffuse. So you can activate thermally at 8 or 9 Kelvin, but below 8, 9 Kelvin, it's almost 0. So I have using the diffusion coefficient, I have tried to calculate how much time it would need from this oxygen to move from here to here, classically, or by thermal activation. I have tried to calculate. At 1.6 Kelvin, because that's the range I will be talking today, at 1.6 Kelvin, it takes 6.5 into 10 to the power 31 years. It's years. So universe is only 13.98 billion years, so it's too much, unthinkable. So let's see what happens if we raise the temperature to 2.5 Kelvin. Then it becomes 1300 universe. I mean, just from reaching from here to here, it will take universe 1300 times. And if you raise the temperature to 4 Kelvin, that will be like 1.7 PhD. So I will not be able to even finish one reaction in my whole PhD. So I don't want to do that. That's why we want to move to quantum diffusion. I mean, it will happen by quantum diffusion, but that's why I like this, because I can finish my PhD. So if you think this quantum mechanically, if you think this is a quantum system, then what happens? Then from lattice A to lattice B side, it doesn't need to go through the classical barrier. It can just tunnel through. This is very fundamental quantum tunneling, that it doesn't need to go over the barrier. It just can tunnel through the barrier, and it can show up at a different lattice next to that first position. So it can move from lattice A to lattice B, and it can also do chemical reactions by quantum tunneling. So classical reactions that needs to go over the barrier, but quantum mechanical reactions, or if reactions happen by quantum tunneling, it can just tunnel through the barrier and reach its product state. So it doesn't need that. This tunneling process is temperature independent. So that's the beauty. So we can study at this low temperature all these reactions because it happens by quantum tunneling. So how do we study? We use FTIR. So anything we want to study, it needs to be FTIR active. So for example, this is one of the classic experiments in this field. So this is what they have done. They have produced hydrogen atom inside solid parahydrogen, and they have reacted with NO to make HNO. So the first thing, if you want to have any chemical reaction, you need two things bring closer or just next to each other. Otherwise, there will be no reaction. That's the first thing we learned in general chemistry. So for chemical reactions to happen, like NO and H, this H needs to go over there. And we know that can happen by quantum tunneling. And what they have done, they have produced, they have produced hydrogen atom by photolysis. So before photolysis, they only had NO inside the matrix. Then they have photolysed. So during photolysis, they have produced some HNO. So that's the HNO peak, IR absorption peak. Then they kept it in the dark. So if you keep in the dark for like 155 days, that means 2.5 hours. So in 2.5 hours, that HNO grew. So to grow HNO, you need these H atoms to come closer to this NO. So they have proved that over this 2.5 hour, hydrogen atom was diffusing and making HNO. So if you have a reaction like this, and if you follow with your FTIR and estimate the reaction rate constants, K, you can convert it to diffusion coefficient by this equation. We'll do that a lot later. So let's see how the mass effect on this quantum diffusion process. So I mean, this is complex because we don't have a square barrier, but let's simplify and see a square barrier. So if you have a square barrier, what would be the rate for your tunneling? So that tunneling will have this inverse relation with the mass exponentially. So there is an exponent. So I try to calculate or estimate for few atoms and molecules, hydrogen, deuterium, oxygen, hydrogen fluoride, water and chlorine. So you see for hydrogen, if we normalize as hydrogen as 1, so all of them like oxygen, water, chlorine, for these heavy atoms or molecules, that diffusion process or that tunneling rate should be almost 0. So it's hard to see the numbers here. Let's look at the table. If hydrogen has 1, expected tunneling probability or tunneling rate should be orders of magnitude slower. So for hydrogen, if it is 1, then for chlorine it should be 10 inverse 4. So that means it's 4 order of magnitude slower. So that's the case theoretically. What is experimentally? So experimentally, all these molecules, atoms, and pseudoparticles, they have been studied as quantum tunneling or quantum diffusion. So here I'm showing 3, hydrogen, deuterium, and hydrogen fluoride. So hydrogen fluoride is heavy, like 20 times heavier than hydrogen atom. They have found that, one group found that hydrogen fluoride can diffuse in solid parahydrogen and by quantum tunneling at 4 Kelvin, to be exact 3.6 Kelvin. And if you look at the diffusion coefficient, for hydrogen it was 1.7. I mean, I'm multiplying by 10 to the power 16. That I will do whole day. So you can just, if you don't look at the unit, this is, you can compare for other things. So if you compare for hydrogen and hydrogen fluoride, you'll see that 1.7 to 0.44. But we expected if hydrogen is 1.7, for hydrogen fluoride it should have been 0.0025, 4 order of magnitude slower. But that's not the case. It's only 1 order of magnitude slower. So that's very surprising why hydrogen fluoride is fast diffusing in solid parahydrogen. And that's been done, D atom has been done in deuterium, and that was slow. In deuterium, because deuterium solid is less quantum mechanical, so it should be slow. We know that. So that's fine. Now let's move into our system. We wanted to study that, okay, they have found hydrogen fluoride. We all know what is going on. And they knew for hydrogen and deuterium they can diffuse. We wanted to know if we can study some other atoms, heavy atoms, we call them. So our temperature range, I already have told you that 1.5 to 4 Kelvin, that's we can access. And when we make a matrix, what we do, we make a solid parahydrogen matrix. Inside that solid, we put some dopant. It could be carbon monoxide, chlorine, sometimes CH3D. So when we deposit our sample or make a matrix, we don't make 100% HCP matrix. We make like 60% HCP and 40% FCC. But we can anneal that at 3.5 Kelvin. So we anneal our crystal at 3.5 Kelvin. We have friends who actually anneal their sample at 900 degrees Celsius. So that means 1100 Kelvin. So we anneal at 3.5 Kelvin. And when we anneal, we can achieve 100% HCP. We call it nice crystal or anneal sample. And if we don't anneal, we call it as deposited sample. So there is a term we use, XHCP, that will give us the fraction of HCP content in the system. Then we fertilize with our, we have laser, 193 nanometer laser, and also sometimes we use UV, 365 nanometer UV, that we can fertilize different molecules inside solid parahydrogen. So, as talking about photolysis, we fertilized oxygen. So if you fertilize oxygen with 193 nanometer laser, you'll make triplet P oxygen, which is the lower energy or lowest energy oxygen atom. So we make oxygen atoms. Those oxygen atoms can react with oxygen molecule to make ozone. So why? Because if you look at the orogeniity surface, if you have oxygen and oxygen molecule, they almost have no barrier, and it falls covalent minimum here. So it's easily made ozone. So we see ozone, and so we're fertilizing this inside hydrogen, like sea of hydrogen. So inside that sea of hydrogen, that oxygen triplet P, it doesn't have the energy because it's an endothermic reaction. So at that low temperature, you cannot do any endothermic reaction. So this reaction doesn't happen. So it will not make any water or OH or anything. But if you fertilize ozone, then you can make singlet D oxygen, which is high energy oxygen. They can react with hydrogen to make OH, then it will make water, then it will make HOO and everything. So in our study, we want to study this reaction, oxygen plus oxygen molecule. So as we want to study that reaction, we want to avoid all these reactions. So that's why we need to optimize our system. That took us some time to optimize what is the best time, because we want to make some oxygen atom, but we don't want to fertilize our ozone. So that's we did for some time, and we optimized, and now we can study this reaction. So when we study that reaction, we study actually quantum diffusion of oxygen atoms in solid parahydrogen. Now let's talk about that. So in this experiment, we have deposited some oxygen molecule. Then before fertilization, we took FTIR spectrum. You see there is no ozone. This is the ozone region of IR absorptions. And before fertilization, we see no ozone. This is the concentration of ozone. And that gray bar is the fertilization time. During fertilization, we have produced some ozone. And you see just after fertilization, we have some ozone. But when we keep the system in the dark, what we see, these ozone peaks grew over these 11 hours. And if you look at the concentration, it also grew over time. Classically, this reaction should not happen. It should have been like this broken line. But what we see, ozone is growing over time, and ozone is growing up here. So what is happening? I'm showing a cartoon. This cartoon maybe not the exact depiction, because we are talking about all quantum mechanical systems. Let's see the cartoon as well. So if we are fertilizing with 193 nanometer laser, and this is our matrix. So these are oxygen molecules. So this is too much concentrated. Actually, in our system, it's not like you'll find oxygen next to 2 lattice site apart from another oxygen molecule. It's like 14, 15 lattice site apart. So this is not exact depiction, just a cartoon. So if we fertilize, we can make oxygen atoms. If those oxygen atoms can reach an oxygen molecule, they will make ozone right away. But if they reach somewhere in interstitial spaces, they should stay there according to classical system. But this is not classical. This is happening by quantum tunneling. So somehow this oxygen atom can move around and find more oxygen molecules and makes more ozone over time. This is at this temperature. We don't expect that, because thermal activation you saw that at this temperature, this is 1.6 Kelvin. At this temperature, it should take like 10 to the power 31 years, which is not possible. So that means this is happening by quantum tunneling. It doesn't thermally activate. So what we are seeing here, the ozone growth. Now, if you look at this reaction, that's a bimolecular reaction. So you can have a second order rate expression, but we have very high oxygen concentration. So we can make it pseudo first order. So if you make pseudo first order rate expression, you can solve it easily. And this is the expression we use to fit this data. So if we fit this data, it fits very well. You see that black line? Then we can get our reaction rates. When you have reaction rate, I already have showed that you can diffuse, you can get the diffusion coefficient as well. Because I have showed that equation. So now you can get the diffusion coefficient. Let's again compare with hydrogen. So hydrogen, it was 1.7 into 10 to the power minus 16. So now, if you compare with hydrogen, this oxygen at 4 Kelvin, so I'm comparing at the same temperature closely, 4.2 and 4 Kelvin, that's like 0.81. So it's not like it's dropping by a lot, because if you remember, it should have been 3 orders of magnitude slower. But we see only half slower. It's not any order of magnitude, just half of hydrogen atom diffusion. So this is surprising that oxygen atom can diffuse. This is heavy atom. Then it's only, the diffusion coefficient is only half. So that means it's diffusing very fast. So we are studying, so we wanted to understand more. So we studied against morphology and temperature effect on the diffusion. So what we saw here, if we make a matrix, and as deposited matrix, where we have XHCP on, that means HCP content is like 60%. then what happens, we see the reaction is almost done, but if we raise the temperature, we start to anneal. When we anneal, what we see is new ozone growing. So where is new ozone coming from? So after doing some analysis, we have found that if you don't have a nice crystal, like 100% HCP, if you have 60% HCP, 40% FCC, that will trap some oxygen atoms. And that will slow down your reaction and also trap some atoms which can be released by annealing. So let's look at the reaction rate constant for this system. So these blue ones are as deposited samples. That means not so nice crystal. But these green and red, those are nice crystals. So from 1.7 Kelvin, not so nice crystal, to 1.7 Kelvin nice crystal, what we see that the rate constant for these reactions goes up. That means if you have a nice ordered system, the reaction is faster. Well, not so surprising, because if you have ordered system, quantum tunneling will be better. But surprising thing is, these two, both of them have ordered system at 4 Kelvin and 1.7 Kelvin. So we raised the temperature by double, but what we saw that diffusion coefficient or rate constant didn't go up. So that was very surprising, because if you raise the temperature, you should expect that your reaction rate will be faster. But what we saw, reaction rate was not that fast. So that was an interesting result, but if you think quantum tunneling, it is temperature independent, so it should not depend on temperature. That's why we see these temperature independent. So that actually proves our point that quantum is happening by quantum tunneling. So here, I already have talked about here that what should be the diffusion coefficient. So if you look at the diffusion coefficient as deposited sample, not so nice crystal, 0.32, but if you anneal, that's 0.76. But if you raise the temperature, that's very close, 0.76 and 0.81. That's almost equal. So now we are like, okay, we were studying in a very quantum mechanical system, solid parahydrogen. Let's move into a less quantum mechanical system, which is orthodeuterium, because we have access to that. So if you see the Debord parameter, orthodeuterium is less than parahydrogen. We did the same experiment in orthodeuterium, so which is less quantum mechanical. What we see the same thing. Ozone is growing after we keep the system in the dark after photolysis. Those oxygen atoms is moving around, finding new oxygen molecule, making ozone. So same thing, we can feed the data, concentration data to get our rate constants, and we got that. So as we are doing temperature things in parahydrogen, we want to do that in orthodeuterium as well. So here you see two temperature range. So we didn't do hundreds of experiments again. We just did 4 experiments, I guess. So where we varied the temperature as well. So when we have varied the temperature, what we saw that it doesn't change a lot. It feels like that blue ones are at low temperature, red ones are at high temperature. It changes a bit, but it's not that much. Let's look at the numbers. So diffusion coefficient at 4 Kelvin and 2 Kelvin, 0.11 and 0.09. It's not too different. It's almost close, 0.09, and we have, if you put the error bar and if you do 10 experiments, I guess it will just come closer like it did for parahydrogen. Now we can compare, in orthodeuterium, we can only do as deposited experiment. We cannot do annealed experiment. There are some experimental constraints. So we compare our oxygen in orthodeuterium to parahydrogen. Let's compare here. So at 1.8 Kelvin and 2 Kelvin, let's compare these two. So, sorry, I had animation. Yeah, so if you compare these two, 0.09 and 0.81, 1 order of magnitude slower. But it's not too slow, because in parahydrogen, it was 0.81, in orthodeuterium, it's like 0.09. It's not that much slow, it's just 1 order of magnitude slower. But if you remember, for deuterium and hydrogen, from parahydrogen to deuterium, it was like 1.7 and that was 10 inverse 5. So now, we're getting something completely different. What they got for deuterium, it was slow, but it was much slower, like 5 orders of magnitude slower in deuterium. But what we see, we don't see a big change, we just see 1 order of magnitude slower. So that's a big question, what is going on? So we'll talk more on this. So, okay, so we went from quantum mechanical system to less quantum mechanical system. We wanted to go even heavier atoms. So if we go to heavier atoms, what happens? That we wanted to see. So we wanted to, so next natural atom from oxygen would be chlorine, because oxygen has 16 mass, then chlorine has 35. The main thing is we can access the chlorine easily and best. We understand chlorine. I mean, we have many papers from our group, chlorine atoms, chlorine molecules inside solid parahydrogen, so we understand it very well. That's why we chose chlorine, but we wanted to study with carbon monoxide. So this reaction will be chlorine plus carbon monoxide to make ClCO. So what we do, in our group, we have developed all this system. I'll show here. Not me, the students before me, they have developed this. So if you fertilize chlorine molecule inside solid parahydrogen with 365 nanometer, what happens, it makes chlorine atom. Fine, it's not hard to make. But those chlorine atom inside a sea of hydrogen. So you expect that it will react with hydrogen. But what we see, what our group saw, that this chlorine atom does not react with hydrogen if you don't excite those hydrogen. So how do you excite? You just excite vibrationally. So usually, let's look at the energy system. So if you have chlorine atom next to a hydrogen molecule which is not vibrationally excited, it's ground state, then what happens? It cannot react to make HCl and H atom, because you have this energy, I mean, this is endothermic by 360 wave number. There's a very small tiny bit of energy, but still is short. So at that temperature, you cannot put that energy, so this reaction will not happen. But this is a very interesting way to do reaction. You vibrationally excite the hydrogen molecule. So if you excite this hydrogen molecule vibrationally, its first vibrational excited state, then these chlorine atoms will react with hydrogen molecule, and over the barrier it can just make HCl and H atom. It's easy. That means what you can do, if you excite your matrix, how do you excite? We use near infrared light. So hydrogen actually absorbs at 4100 to 4500 wave number. So if you put that energy, I mean those infrared lights onto your matrix, you excite the hydrogen and this reaction will happen. But if you block them with some filter, we use a filter, we call it LPF filter, LPF, low pass filter. So if we use that low pass filter, if you block all this near infrared, then this reaction will not happen. So now you have chlorine prepared inside the matrix by photolysis and it's not reacting. So that's nice, we want that. But if you expose it to near infrared, it will just react. So we just, that's how we keep our clean chlorine atoms inside solid parahydrogen. We put some carbon monoxide with those chlorine, they will react and they will make ClCO. So yeah, here you see we have made chlorine atoms and we already had CO that will react to make ClCO. But if we block the near infrared, it will not react. If we don't block, it will react. So let's see, there is nothing new because you already know what's happening. So before photolysis, no ClCO because we did not put any ClCO, it should not be. Just after photolysis, it started to produce because it's 2 minutes or 3 minutes after the photolysis. And after almost 10 or 11 hours, you see we have produced a bunch of ClCO. So let's look at the concentration plot. We did this experiment at 4 Kelvin. This is 365 nanometer photo or photolysis. And this is NIR exposure, this red bar. So now let's look at, first let's look at HCl, this bottom one. There was no HCl until we have exposed it to near infrared. CO, this is CO. CO is not reacting a lot. That's why our CO is almost constant. Then if you look at ClCO, it was 0 before the photolysis. Then after photolysis, it grew over time. from zero, almost zero. So it grew over time. So this is quantum diffusion, because chlorine atom cannot move classically, because it's 35.5 times massive than hydrogen. So we don't expect any other way than quantum tunneling. So this is definitely quantum tunneling, these chlorine atoms diffusing and reaching to carbon monoxide, making ClCO. So we can do all the kinetics, I already have showed you before, but another interesting thing happened. When we expose it to near infrared, those ClCO starts to drop. It gets destroyed again. So near infrared not only allowing this chlorine plus hydrogen reaction to make HCl, you see HCl is growing, it also somehow destroying our ClCO. We'll investigate that in next few slides. So before going into that, let's look at the temperature. So in this experiment, what we did, we have done our first part of the experiment at 1.6 Kelvin. So at 1.6 Kelvin, you see ClCO was not growing. But when we raised the temperature to 4 Kelvin, what happened? ClCO started to grow. So it could be that at 1.6 Kelvin this reaction stops, or it could be that at 1.6 Kelvin the yield is low, so we are not seeing that. So we did another experiment where we increased the concentration by a lot. So if you look at the concentration, that's like chlorine atom concentration 130, then carbon monoxide is also 130. So these two experiments are similar. Just one thing is different. Red one is high temperature 4 Kelvin, and blue one 1.6 Kelvin. So if you compare these two, it looks similar, right? Everything is similar. But if you look at the scale, at 200 minutes we have produced only 0.05 ppm of ClCO. But at high temperature we have produced almost 0.8 ppm of ClCO. That means we have produced almost, I would say 20 times, almost 18 to 20 times more ClCO at high temperature. So let's look at the yield, all the yields. So at high temperature, those red ones are high temperature yield. So that's like 1.2%. If you take the average, that would be 1.2%. But at low temperature, the yield is like 0.1% or 0.15%. So our yield at high temperature is like 10 or 15 times higher. So that's telling us something, that at high temperature, this reaction has better yield than at low temperature. But that's not very surprising. Whoever does chemical reactions, if you increase the temperature, sometimes yield goes up. So it's not very surprising. But not surprising, the question to ask is, why is only 1.2% yield at 4 Kelvin, or only 0.1? Because we have other 98.8% chlorine left inside the system. We have carbon monoxide. Why they're not reacting? We don't know the answer to that question. So yeah, let's look at the temperature as well. So here we see a big temperature difference. The blue one at 1.65 Kelvin, red one at 4.02 Kelvin. So we see a good difference for this chemical reaction. But this is not exponential difference, because if you look at the diffusion coefficient at two temperatures, like 4 Kelvin and 1.7 Kelvin, it's like 0.5 and 0.15, 4 times bigger, or 3.5 times bigger. So usually, this temperature dependence should be exponential, because Arrhenius law tells us that it should be exponential. But we see this is not exponential growth. So, exponential up by temperature. So as it is not exponential, that's also telling us this is not Arrhenius type system. This is non-Arrhenius system. We'll have to deal with something else, not Arrhenius equation. So as you remember, we were talking about the ClCO decay. It was decaying. So how that was decaying, let's investigate. So what we have in the system, when we expose it to near infrared, we have near infrared light, we have excited hydrogen molecule, and we also have hydrogen atoms moving around, because we have produced some hydrogen atom by that reaction, because we have excited our hydrogen molecules. So what can happen? First thing can happen is hydrogen atom can react with ClCO and make HClCO. That's an exothermic reaction that has very strong ion absorption, but we have never seen HClCO molecule inside our matrix. We looked for that, we didn't see that. So that's why we rule out the first one. The second two can happen because we have excited hydrogen molecule which can react with ClCO and make HCl and CO, leave a hydrogen atom. So when you break ClCO somewhere and make HCl and CO, those two will be just closer, right? So you can find out those molecules by looking at the clusters, because if they form, they will make cluster because they're forming at the same place. So they will form the cluster, and with IR, easily you can look at the cluster if you know the wave numbers, or you can predict the wave numbers. Another way is if hydrogen atom react with ClCO and make HClCO, in both cases we'll see the clusters. So let's look at this experiment. Again, this is photolysis, and the red bars are near infrared. So if we have near infrared, so what's happening here? CO, this is HCl, this is ClCO, and this is the cluster peaks. So here I'm showing just the absorbance. So we're seeing our normal ClCO growth. When we expose it to near infrared, it starts to decay. When it starts to decay, let's look at what happens to the HClCO state. We see that HClCO is growing. That means one of them can happen. I mean, one of these two can happen. Then we stop our near infrared after 30 minutes. What we see, our HClCO is still growing. At this point, we don't have any excited hydrogen molecule. We only have hydrogen atom. That means this white part, that only can happen by if hydrogen atom react with ClCO. So that means our third reaction is definitely happening. But when we expose it to near infrared again, we see HClCO grows again. When it grows again, what we see, this growth is faster than before, because here you see the slope is slower and this slope is bigger. So that means it was faster. So now the problem is, as it is faster, if it is both, it is faster because both are happening, or because we are producing hydrogen atom at this point again, so we have more hydrogen, so that's why it's faster. We don't know, and we don't have an experimental way to isolate that. So we see that, so both of them actually can happen, but for sure, the last one, hydrogen atom reacting with ClCO, that's definitely happening. So we could not exclude the middle one, but we could confirm the bottom one and exclude the first one. So another thing we have found here was when we expose it to near infrared at high temperature, what happens? ClCO decays. So this is ClCO concentration. But at low temperature, what happens? ClCO goes up, then comes down. So if you zoom in here, what's happening? ClCO is going up, then coming down. That means what we have found from here, if you have excited hydrogen, if you look at why it's going up, that means somehow ClCO is growing again or producing more ClCO. So you have a reaction where ClCO is producing, another reaction where ClCO is breaking, because we know we have near infrared. When you have near infrared, it will break. So it was breaking to HClCO. So what we think now, that we have studied this reaction for long, from 2006, that chlorine atom will react with excited hydrogen, but sometimes what we have found here, sometimes those excited hydrogen molecule will transfer the energy as momentum transfer. That momentum will give those chlorine a kickoff, and they will shoot off to reach another carbon monoxide molecule or something else to do some other stuff. So now we have two channel, reactive channel, which we have studied for a long time, to produce HCl, produce chlorine atom. Now we know if we expose it to near infrared, that will give a non-reactive channel for some of the chlorine, which will just transfer the energy for shoot off inside the matrix. So I will end here with this one. So we have studied chlorine atom diffusion for many experiments, you see. So here I'm plotting all the rate constants. On the left, that's rate constants. On the right, same data plot, just different scale, so it's diffusion coefficient. What we have found that if we plot those diffusion coefficient or rate constant against our impurity concentration or dopant concentration in the system, we see that our diffusion coefficient goes down over time. So this is inversely proportional. If you increase the concentration of the system, concentration of the reactants in the system, reaction slows down. This is never going to happen in classical kinetics, but why this happened? We think what's happening is happening by quantum tunneling. So when you have quantum tunneling, let's say you have a nice crystal, single crystal, one chlorine atom. If they diffuse through the crystal, it will go from one lattice side to another side without changing the energy state in there from lattice 1 to lattice 2. We call it resonant tunneling. So resonant tunneling is faster, but if you have some impurity, that will perturb your crystal field. So when it is perturbed the crystal field, that will be like, if you have a chlorine here, that chlorine wants to go this way, but now it needs to go up here. So it doesn't have that energy resonance anymore, so it's non-resonant, that's why it slows down. So if you increase the impurity concentration in the matrix, it slows down because you have all these non-resonant diffusion process. So in the conclusion, I want to say 3 things. First is, we have found that heavy atom can diffuse in solid parahydrogen and orthodeuterium, which is not been known before. Hydrogen atom was known for 50 years, but this is the first heavy atom we have reported. And you can use those to study chemical reactions. And we have found that's very surprisingly fast. We don't know exactly why. We have some speculation, but we don't know why. It could be something big, or it could be something not so big. That there is very fundamental something about quantum diffusion what we don't understand. And also, we have found that our diffusion coefficients or rate constants are inversely proportional to the impurity concentration. So for this, what I'm proposing in my thesis is that, as we have seen this for all my projects, whenever I have studied this, in every project we saw that inverse relation. So what I am proposing in my thesis that whenever you report a diffusion coefficient by quantum tunneling or reaction rate by quantum tunneling at this low temperature, you should report temperature, and you also should report the concentration of the system, I mean dopant concentration or impurity concentration of the system. With that, I want to thank all the funding organizations, chemistry department, NSF, NASA for funding my PhD. I want to thank my supervisor, Dr. David Anderson. He helped me all these 4 years, and my committee for their time and support, and also my lab mates, Aaron, and Elvis, and all the undergrads, and also my PCAM buddies, PCAM seminar buddies, because they helped me to grow over this time. Some of them are here, thank you. And also thanks to my family and friends, especially the Bangladesh community here, they helped me a lot. And also thanks to my wife, Tasnimara. Now if you have any questions.
Yep, so any questions for Ibrahim? This is your one chance. He's leaving.
I may have covered everything.
Crystal clear. All right, well then, let's thank Ibrahim for his presentation. Thanks.
Good job doing it in 50 minutes.
Yeah.
So now we remain.